So what I want to do next is I want to talk about p-series, which is a particular application of the integral test. And a p-series is a series of the form 1 over n to the p, where n starts at 1. Okay, so this is the sum from 1 to infinity of 1 over n to the p. This is all stuff that you've seen before in Calc 2. And it turns out, of course, that this converges if and only if, so this converges if and only if p is greater than 1. So if p is greater than 1, it converges. If p is less than or equal to 1, it diverges. Okay, and so that's the p series there. And this all comes down to evaluating the integral test. So if you were to have the integral of 1 over x to the p, you know that this is also going to converge. This converges if p is greater than 1 and diverges otherwise, right? This comes exactly from that, and you can fill in the details by evaluating this integral on your own time. So I would encourage you to fill out the details here. One thing that I think is worth emphasizing is the harmonic series. Okay, so the harmonic series. The harmonic series is just the p series with p equals 1. This is, of course, well known to diverge. And you could, for example, compare it to the integral of 1 over x as x goes from 1 to infinity. And so this is going to behave like the natural log of x as x goes from 1 to infinity. And I guess if you wanted to be super rigorous and super careful, you'd have to write this as an improper integral, take the limit as t goes to infinity of the natural log of t, but this is going to be the natural log of infinity, which is infinity. Okay, so in other words, what I'm saying is slightly imprecise, so I better be careful here. This is the limit as t goes to infinity of the natural log of t as your value t goes from, as x goes from 1 to t. Okay, so this is going to end up being the limit as t goes to infinity of the natural log of t, okay, which is, of course, infinity. Okay, but that tells you roughly how 1 over x grows. And it turns out to be a really good estimate for its asymptotic growth. It's going to grow like the natural log. So the integral from 1 to, say, capital N of 1 over x dx does really behave like the natural log of capital N. Okay, that tells you exactly how quick this function is going to grow, and that tells you roughly how quickly that function is going to grow because we have those following bounds that we talked about in the integral test. So that's the harmonic series. One other thing I just wanted to mention is what is called the Riemann zeta function, which is a super complicated topic, but we can at least talk about, a few things here. So if I were to have zeta of p, this is going to be the sum of 1 over n to the p, which we know converges if p is greater than 1. But one of the things that we're actually going to do, and one of the insights that Euler had, or that Riemann had actually when he was studying this, is he said, don't plug in real values, p, plug in complex values, s, okay, where s is going to be sigma plus it. And it turns out that this series converges if sigma is bigger than 1. And there's a lot of really in-depth, hard-hitting complex analysis that's relevant here. So there's what's called a continuous, analytic continuation. And what that means is that this function, zeta of s, is going to end up being holomorphic whenever sigma is bigger than 1. And then you can define it differently other places. But it's kind of like when you were to have, so if you were to have a function here, something like that, what you want to know is what are some ways that you can continue this function. So let's say it just stops here, so it's not differentiable at the endpoint. But what are some ways that you can continue this function so that this function continues to be differentiable, so that it's still smooth? Now, you could continue this function in lots of ways. For example, you could have it come down like this at a sharp point, but then you're going to lose differentiability. So you have to be a little bit careful about how do you keep the smoothness and so on. And that's some of the detail that's there. That's it's a gross oversimplification, frankly. But the Riemann zeta function involves what's called analytic continuation, which we're not going to talk about any further. But you can look it up on your own if you like. So this Riemann zeta function, zeta of s, is defined as 1 over n to the s, where s is this complex number, sigma plus it. Okay, and of course, when s is a real number that's bigger than 1, then it's just a p-series. We know everything about it, basically. That's not true. We don't know. There's actually a lot that we don't know about it. For example, it's not clear whether the sum 1 over n to the 5 is rational or not. Okay, so it's unclear whether or not this number 1 over n to the 5, whether it's rational or not. You're never going to be able to determine whether it's rational or not by calculating arbitrarily many terms, because whether or not it's rational depends on all of the decimal places that you have. Is it repeating? Is it terminating? And until you calculate all of them, you're never going to know that for sure. So calculation alone is not going to answer this. But this is a currently famous open question. It's not known whether or not this is even rational. It is known that if you have 1 over n to the 2k, then these are kind of the even analogs. So like 1 over n squared, 1 over n to the 4th, 1 over n to the 6th. It is known that these behave like pi to the 2k over some rational number. Okay, so over some rational number. Okay, so that is known. There's a lot that's not known about these odd counterparts. So even something like 1 over n to the 5th, the irrationality of the sum of 1 over n cubed. So 1 over n cubed. This wasn't known until very recently. By very recently, I mean the 70s. This is called Apéry's constant, or Apéry's theorem. And it turns out that this value, that 1 over n cubed, is irrational. Okay, which is a pretty remarkable thing that was proved there. But anyway, so there's a lot that we don't know. But yeah, I think that's enough of a digression for now.